It's going to be the second presentation in the applications section of today's symposium by Daniele Marinazzo, who is a professor at the Department of Data Analysis at the University of Ghent in Belgium. He's a statistical physicist focused on methodological computational aspects of neuroscience and on dynamical network subserving function. His group develops new techniques for inferring connectivity architectures from the dynamics of recorded neuroimaging data. Relevant papers or works for this workshop are Advancing Functional Connectivity Research from Association to Causation, and his multiple contributions to advancing Granger causality, for example, in multiscale Granger causality. So once we're set up, we very much look forward to your presentation, Daniele.
Thanks a lot. So I sent a link to the presentation in the chat, which you can download.
Yeah, can you send it to the other one? There is one with the logo.
The one with the logo, sure.
Yeah,
okay. This one?
Yeah, perfect. I got it. I'm going there. Oh no, Dropbox. Okay.
You can just download it. You don't have to save it to any Dropbox. It's just a link.
Hey, yeah, awesome. Okay, so I opened it and I can now download. Okay. Oh. Okay, so at least I'm presenting for us, and now I have to share the screen and everything will
Great, thanks.
No problem. Is it working
okay
now?
Yeah, perfect. Thanks a lot. So without further ado, let's move on. Sorry about this. Actually, I don't know what would have happened, but anyway. So I would really have loved to be there in person and see good and old and new friends, but feels like we are anyway together. Thanks for organizing this. And yeah, so even though I now learned that this is the application part, it will be more general to some extent, at least for my standard. Still, there will be some applications. I hope it fits your taste. So please, Jason, go ahead. So indeed, when we studied the brain, mostly, I mean, this is an example to the macro scale, but we can do a similar reasoning for the micro scale. So we have some structure, we have some activity, we have some pattern of correlated activity, and ultimately we are after the functioning of the system as a whole. And the system as a whole, we know that implies that different areas, and the areas can be macro areas like in the figure or smaller portions, but actually this is also the case when we study social systems, and these are individuals, let's say. We're talking about making sense of how they behave together, in synergy. Next slide. So this synergy happens at multiple spatial and temporal scales. I guess you have seen different versions of these figures in the last years. So we have different types of networks. So the figure from Olaf's book, of course, is focused on networks, and now we'll see what we mean when we talk about networks. And then again, we have synergy at different scales and at different spatial and temporal scales. Please go ahead. So we can take as a paradigm of this seminal thoughts what happened in Edelsman lab and is let's say PhD students Giulio Tononi and Ola Sports, who, let's say, took different and complementary roads, focusing around these ideas of the interplay between differentiation and integration, one focusing on connectivity in terms of networks in the brain, and the other about joint information in the study of consciousness. Please go ahead. And so indeed, this integration and differentiation are not some things which are antithetical, but they can coexist. So please go ahead. Now, in our field, we witnessed an increase not only of functional connectivity, which is actually a word that, I mean, as also Conrad said, that we basically made up to show to represent something beyond the methods which is obtained, usually correlation, but then also things like network, connectonics, connectome, etc., have now basically taken over a bigger and bigger portion of our scientific discourse. Next. So we can see networks as starting from their two main characteristics. The first one is network as pathways. So we have here the famous Königsberg Bridge, which is told to have led to the birth of network science. Next. And indeed, well, this would not have happened today since they added another bridge, so the problem would have become trivial. And then, please, next slide, we go to the second characteristics of a network. So a network is an expression of collective dynamics and function. So things that work together towards a certain goal. And so let's keep these two definitions in mind, because then it will become important when we try to make sense of what those links are. Next. So indeed, especially talking to referring to this second characteristic, this integration view, so of a system behaving differently than the sum of its part, we have some examples from the past centuries. So starting from Quetelet, which was, by the way, from Ghent, where I work. And he was a kind of big data scientist ante litteram, because he was after looking for some general characteristics of the populations by looking at several aspects. In particular, he was interested in body mass index, and then in the criminal attitude of people, in particular concerning free will. And so indeed, one of his ideas was that any behavior, in particular criminal behaviors, is just a fluctuation of an average behavior. So we are not considering the individuals in particular, but we are considering the society, which has a behavior with some deflections. And this is also important for what has been said so far and what we will say later. So whether we really care about all the interactions that might, for example, or the particular individuals who could commit a crime, or the fact that a crime will happen or will be committed as a part of a general trend of the society. Then is told, this also is not 100% verified, but at least it was in the air, we can say, that Quetelet thought could have, let's say, have an influence on Maxwell in his statistical theory of gas. And then we move to neurons, and in particular to the Nobel Prize shared by Golgi and Ramon y Cajal, which came from two different roads. One succeeding in isolating individual neurons, and the other saying, okay, even if we see now individual neurons, behavior arises from all these units together. I mean, maybe to the point that we don't even have to consider these single units. Okay, next slide. So let's go back to functional connectivity and see why actually we might have invented a new word for the correlations. This is something that periodically comes around. So the definition of functional connectivity as statistical association, mostly correlation and then other techniques between measured brain signals, let's say, confuses a bit the map with the territory. So we have some target theoretical properties that we want to observe, and then the methods that we use to infer those properties. So I will expand on this later, but first let's consider, let's say on this part. And so the phenomenon of theoretical interest in all research that uses functional connectivity is basically the interaction among the neural entities, as I said at the beginning. Next slide. As, of course, we can argue whether we are or not in a causal framework whenever we apply some analysis to the data. And then also there, it depends on whether we ask causal questions or we use causal methods and so on. This is basically one of the key points for which we are having this discussion and this meeting, perhaps. Next slide. So here is a sketch from this paper that Klaus mentioned before, in which we sketched three levels which are relevant when we do functional connectivity studies. So we have different levels or different states. So we have a state space constituted by the neural level, then the observational level, and then the inferential level. And we need to navigate across these three levels. And so, next slide. So this is indeed a state space from the system point of view. And the idea is, how do we get to navigate to the space and what we can learn and what not? Next slide, please. So we have here an example in which we have the target theoretical properties. So, for example, two different represented as two different patterns in this hypothesis state space. And then we have indeed two methods, methods A and B, with some methodological properties, and with properties we also say some advantages and disadvantages, and some confounding properties, which we always have. And then by looking at this pattern of correlations, correlation in wide sense, it can be pairwise correlation, it can be something else, we try to restrict our space of hypotheses. So the idea is that anyway, when we address a problem, we have an idea in mind. We have a question, and this question is most of the time a causal question. So we are not just randomly trying to find associations and see what happens. I mean, at least we shouldn't. So once we are in this mindset, this reasoning based on statistical dependencies and its confoundings let's say, could bring us forward towards one hypothesis or the other. Now, here, together with my colleagues, let's say the hypotheses here are really the type of interactions which could give rise to these patterns of observation. This is a starting point. On the other hand, what I will do now in the future, in the rest of the talk, I will try to move on from this point of view and see, okay, here we have some inference on different type of mechanisms which could give rise to those patterns. And then later on, I will say, okay, what if we focus on the patterns alone? So we look at the behavior rather than the mechanism. Next slide. So going back to network, of course, so far, functional connectivity, at least as we meant it in the paper, we had a pairwise network representation, so links between two variables, which could be then conditioning or not. On the other hand, we have some statistics, but statistical, but also fundamental limits to pairwise representation. So as far as statistical limits are concerned, of course, all the confounders and colliders, which is something that is quite common in epidemiology and psychometrics, and much less so in neuroimaging analysis. For example, this work by Mike Cole and Ruben Sanchez Romero, which came out slightly after our perspective before, basically was published in Journal of Computational Cognitive Neuroscience as actually something new. And I mean, it was new to many, and still it is so new that really most of the people kept on doing pairwise functional connectivity and didn't give I don't want to curse now about this. But anyway, it struck me as, okay, but really we are so stuck about correlations that then even something like, okay, consider a collider and maybe things will improve, it's such a disruptive thing. Then Conrad would say, okay, never mind. Anyway, even if you condition on the collider and then if you condition on a variable, then you realize that it was a collider, it's just desperate because you have too many variables. And it's not worth even to pose yourself this kind of problem. And I guess that Conrad is probably right to some extent. Next slide. And then there are some conceptual limits to pairwise network representation. So this is the case of a simple XOR logic gate that cannot be represented as a pairwise network because a single node does not give any information on the target without knowing what the other node is doing. And then in artificial intelligence and machine learning, concepts like synergy, so basically a feature that becomes useful when combined with other and not by itself, is also seen as a kind of weird phenomenon or serendipitous or funny or whatever. Next slide. So in network science, we have higher order graphs. So in which a link connects 3 or more variables. And this is the case, for example, now in your room, if someone is infected, then it doesn't make much sense to say, okay, Stefano is infected and then is connected to Kayson, to Klaus, to Beate, etc. and so on. It's an hyperlink in which you are all together. And this is relevant, of course, and is clear when we have some clearly quantifiable links. So people being there together or wirings which are which can be considered as simultaneous between different nodes and so on. And we have a very nice overview published last year on physics reports. Next slide, please. And then there was a perspective which came out last year in Nature Physics, in which, from the point of view of physics, they were trying to make sense of these higher order interactions in complex systems. So the idea was, okay, we have networks. We like networks because they are a compact representation of a complex system. On the other hand, who says that a network has to be pairwise? If you think about it, it's a big limitation because it doesn't have to be like that. Next slide, please. So in that nice paper, they started with the idea of hypergraphs, and then they were looking at higher order interactions in the sense of higher order mechanisms. So variables connected to many others at once, which then make a simplicial complex is called, or an hypergraph, different of these higher order concepts in network science, and this would give rise to higher order behavior such as explosive synchronization and so on. So far so good, but again, next slide please. Starting from this physical point of view, we can ask how can we go from mechanism to behaviors? So this paper came out like last month, and it's about predicting network dynamics without requiring the knowledge of the interaction graph. Now, if you think about it, again, the paper is nice, is very nicely written or so, but on the other hand, if you think about it, we don't need the interaction graph to predict dynamics. Dynamics as a collective system can be predicted by itself. By looking at past behavior, you can see how it goes in the future. You don't need the interaction graph. You need the interaction graph if you want to perturb it. But in order to observe and predict dynamics, you don't need the interaction graph. And more importantly, the interaction graph sometimes can be misleading. For example, in this reply that we that came together to the paper I showed you before, we try to disentangle higher order mechanism and higher order behavior. Next slide, please. So just to make an idea what we mean with by higher order mechanism and higher order behavior, the former speaks to how the system is structured, and one speaks to what the system does. So it means that we look at the observables, we look at the data, and we try from this observation to look at behaviors, which can be of higher order or even pairwise if you want. But in this case, it was more about the higher orders. And we focus on the behavior and not only on the underlying structure as a complementary thing. And also because we know that there is a lot of degeneracy and there is a lot of confounding in this. And so we start from the behavior. So from what in a Conrad example at the beginning of the talk was our neural or language prediction model, ANN, and what's one other. Go ahead. So in this case, for example, we have two examples. Two examples in physics of coupled spins. So we have some spins that can be coupled either by pairwise links or by hypergraphs, so by higher order links. And so here we have an Hamiltonian. On the other hand, the behavior, it's ruled by this probability distribution of all the variables together. And indeed, we can have higher order behavior only from pairwise links. This is a simple example of a frustrated spin system in which basically we have three spins that when they are coupled, let's say the third spin receive conflicting, let's say, information from the other two, so the system is thought to be frustrated. And indeed, by using the total correlation, so the sum of all the information is higher than the sum of the individual information. So here we have a higher order behavior which arises from low order, so from a pairwise coupling. Next slide, please. Moving back to neurons, we know that higher order effect can make a difference. So, for example, there was a paper by Scheidman and Bialek, so which in which basically they saw that in pairwise correlation, you could look at, you could decode some visual input. On the other hand, by fitting different model, pairwise model, max entropy model, and so to the data, we saw that when the stimulus was richer, in this case, natural images, we had a higher order interaction, which let's say, which didn't fit, so the pairwise model did not fit the data anymore. So we needed higher order interaction to decode more complex stimuli. Next slide, please. So we can focus on two basic types of higher order dependencies. One is redundancy and one is synergy. So this is a slide by my colleague Fernando Rosas. And since everyone here has fun using DAL-E, etc., next slide, I try to generate redundancy and synergy. So in the first case, it gave actually something quite similar. So this linear geometry for the redundancy, and people all dressed together likely like this one. On the other hand, again, for the synergy, there was this circular mechanism of something that converged to something more than the individual part. Next slide. And again, going back to the slide before, we were talking about differentiation integration and in networks, and I was using this slide for a long time now. But then, next slide, Olaf finally, in this perspective, published 1 month ago or two, realized that information is the missing piece in connectivity and dynamics. So, and of course, I'm joking. I guess that Olaf realized much earlier, but indeed, in this perspective, for the first time, he put together connectivity, dynamics, and information in the sense of multivariate probability distributions that we are talking today in this paradigm to solve the complexity of the brain. Next slide, please. So just briefly, information is the amount by which one variable, in a wide sense, can be an answer to a question, signal, measurement, reduces our uncertainty or surprises us about another variable, or for what is worth, even about itself. Next slide. And so this is quantified using logarithm and probability distribution, and here we have schematics in which we have the basic quantities of pairwise interactions. So we have the individual entropies, we have the conditional entropies, we have the joint entropy, and then we have the mutual information, which can be defined either as the sum of the two individual entropy minus the joint entropy, or one of the two entropies minus the conditional entropy, and this asymmetric variable. Next slide. And then we can extend this to 3 variables. Let's stick to 3 variables for the moment, in which we can have, depending on whether the intersection of the two mutual information comprises all the information of the system or not, we can have redundancy or synergy. And next slide, please. Simple example, we can have redundancy and synergy in information coded by neurons. So neurons responding to complementary or similar features. Then we have examples such as the Markov chains and the data processing inequality are all things that can be seen in terms of interaction information. Next slide, please. And so if we use this interaction information to give a mathematical formulation of this synergistic effect and say that we look at whether the whole is greater than the sum of its parts, we can try to infer something more about the behavior. Next slide, please. So, for example, we can observe that higher order behaviors can arise from pairwise links. So there are two examples. This one in the one below in social sciences by the group of Stefan Turner, and the other one from me and my colleagues, in which we saw that we have some higher order dependency, in particular the fact that is the synergy and not the redundancy which which peaks in the paramagnetic phase, those acting as a precursor of some organized behavior. And this is something that, let's say, is true even when the actual coupling are pairwise. So behavior tells us more about the system than the coupling alone. Next slide. This, on the other hand, a nice study by Andrea Lupi and Fernando Rosas and other colleagues, in which they looked at redundancy synergy in different areas of the brain, seeing that redundancy is more localized in input-output sensory areas and so, and synergy in higher associative areas, and in particular that while redundancy does not distinguish between human and macaque, the synergy is much higher in the human connectome rather than the macaque one. Next slide, please. Of course, we don't have to stop at triplets, because I say, okay, don't stop at pairwise interaction, and then why should stop at triplets? Then, of course, it becomes increasingly complicated. There have been several efforts in the years. One of the first was actually made by Stefano and colleagues in 1999, I guess. And then there were some, or maybe it was slightly later than that, but still was one of the earliest. Then Louis Bettencourt tried to expand the mutual information. We tried to expand the transfer entropy in a quite, let's say, non-parsimonious way. It was hard. And then this paper on a more parsimonious way to expand mutual information came out recently, and then we extended to the conditioning approach, so expanding the transfer entropy slightly after. Next slide, please. So this just as an application, we can see that, for example, in intracranial data recorded in rats, we have the color that codes different areas. And if you look at the redundancy, we basically have a clustering of individual areas. On the other hand, the synergistic multiplets of order 3, 4, 5, and 6 comprise different regions of the brain. Next slide. The same can be seen in a psychological network, so in which we try to make links between the co-expression across subjects of different symptoms, of different responses to questionnaires. Go ahead. So this is the field, next slide, please, of network psychometrics, in which basically people look for latent factors. So, for example, you want to measure depression, but you cannot measure direct depression, so you measure fatigue, insomnia, loss of interest, suicidal thoughts, and so on. In this case, this network should recapitulate these main factors. On the other hand, the psychometric network is nice, but it basically recapitulates the main factors that we already know. On the other hand, extending this mechanism versus behavior thing to psychometrics, we can find an alternative to the latent factors approach, and then we look at the co-expression of data from, so we find hypergraphs from the joint probability informations of these variables. And again, we see that the redundancy acts basically like a clustering, as we saw here. On the other hand, synergy puts together items from different factors. Next slide, please. This is a case, on the other hand, of expansion of mutual information, in which we have a monkey performing a decision-making task, and the neurons have been already classified in classes depending on their mutual information between their activity and the response. So class H and class M are jointly have a high mutual information with the response, and class L does not. And this showed that indeed, thanks, Maria, redundancy stays basically the same for higher order multiplets for all the classes of neurons. On the other hand, the synergy, which is at the beginning very high for class H neurons, which are the ones which are mostly related to the response, then drops. On the other hand, the synergistic multiplets becomes more informative for the other two classes of neurons. Next slide, please. Now, we like network science. We like a compact representation. On the other hand, what I showed you now in the results were basically a mass which look like crop circles, and it defeats the purpose of a beautiful compact representation. And on the other hand, we also want to see, okay, there is a relevant multiplet of information, there is a higher order behavior, but which are the variables which are mostly responsible to this? So we can basically introduce a differential operator on the information and see which, instead of focusing on the joint information of group of variables, we focus on the change of information when variables are added to the rest of the system to form these groups. Next slide. So in this case, both a simple case of Ising spins, again, one system which is central to the other, and is the only one, indeed, spin one, for which you have synergy, so negative gradients of at the critical temperature. On the other hand, for all the other spins take part in redundant multiplets. And also here we have basically pairwise links, but we have first, second, and third order gradients which differentiate this behavior and show which variables, when added to the system, participate either alone or in pairs, contribute to forming these types of interaction. Next slide. Going back to this Neuralinks data, again, we have that pairs of variables form mostly redundant multiplets when they come from the same system, and form synergistic multiplets when they come from different systems. Next slide. So to conclude, mechanism and behavior are complementary aspects. Going back to one of the questions that was asked at the beginning, things like Granger causality or transfer entropy are designed to observe an effect and not the mechanism. Synergy and redundancy are, on the other hand, a natural paradigm to study dynamic behavior and to encompass critical aspects of brain functions, such as segregation, integration, and their interplay. And many things that we use in analysis of neural data, such as dimensionality reduction, manifolds, Markov chains, and data processing, can all be seen under the lens of multivariate information. And I guess I'm done. Next slide. Thanks to my colleagues, and thanks to you for listening.